Hi chemists, this video I'm going to talk about the mole concept. We're at that point where we introduce it. You may have heard of it before, but hopefully this will add some clarity to what you're thinking about. And it is a hard concept to think about. It's definitely something new that most students haven't thought of before. It can be quite abstract too. So I remember when I first encountered the mole in year 11 with my chemistry teacher, and I found it awfully hard going, and so did a lot of people. And it only took now the way that my year 11 chemistry teacher taught it, I just wasn't getting, and a lot of people weren't getting. And that teacher went on leave, and we got a substitute teacher for 2 weeks. I shouldn't say his name, but I think he's at retiring age now. I still see him around occasionally. But he came in straight from the Philippines, I think, or Indonesia. First teaching job in Australia. 2 weeks. And you know what? He fixed it up. He got us on the right track. I think because he chose his words carefully, which sometimes I don't do, and I say a lot of ums. He chose his words carefully, and he took us through us, and he left us after 2 weeks right on track and understanding what the mole is and why it's important. Hopefully you don't have that trouble. Hopefully you can use this resource to get your mind around it, because once you do, and you're kind of on the other side of that mole hill, should we call it a mole hill? That's terrible. Everyone over the age of 60 will have a chuckle. Anyone under, so once you're over there, it's fine, but it's about getting your head around it, okay? And it's not going away in chemistry. It's how we deal with the amount of matter that we're talking about, because grams just don't work. Okay, enough of me rambling. So, our syllabus point, top left yellow, explore the concept of the mole and relate this to Avogadro's constant. Yeah, we're going to learn what that is. And describe, calculate, and manipulate masses, chemical amounts, and number of particles. So this mole concept links masses to chemical amounts and number of particles. And so it goes on to say we need to know the moles of elements and compounds, percentage composition, limiting reagent. It's covering the rest of this chapter basically. So the mole links the amount of the masses of particles, the amount, and the number of particles. Okay, so one of the maths teachers gave me some really good advice here and on this topic. And she said, start with talking about the SI units and revising the SI units, because the mole is one of the SI units. So link it back to there, and all students learn that in science and in maths. So the standard international, or however they say it in French, or the international system of units, because I would just massacre the French. We use them throughout most of the world. Slight dig there. As a common language in science. The 7 basic SI units that you've learnt before are the meters for length, seconds for time, kilograms for mass, Kelvin for temperature, ampere for electric current, and then one of the least known ones, the candela for luminous intensity. And you've also got this new one called the mole for the amount of a substance. Okay, so it's one of the most fundamental units that words, scientists always use, but the public doesn't really. Okay, here's a couple of slides to try and get your head around it. So the mole is a very large number, and it acts as a bridge. I call it a bridge between the atomic level, so the level right down there where we're counting atoms, up to our level, the macroscopic level, where we can see things and things are measured in grams. It's a bridging number between there, because we can't deal with 1 or 2 atoms unless we've got to do a lot of work and a lot of tools, and we finally got there about 40 years ago. But for the rest of us, we need this mole concept because we deal with a large amount of matter. So think of the concept of a dozen, and here we've got a dozen eggs. This word was used to make it easier to express a number of eggs or something that's sold in lots rather than 1 or 2. So everyone kind of knows that a dozen is 12, and it helps us simplify our communication and our counting. So when you order eggs or something, you might order them by the dozen rather than by single, because it's simpler and it's sold that way, and it makes your life a lot easier. So when you're selling eggs all day, the concept of a dozen is very helpful. And when we're dealing with the amount of chemicals all day, we find the mole also helpful. And so it's the same kind of concept. A dozen means a certain amount, and moles means a certain amount. They just mean very different numbers, but they're still meaning the same thing. So instead of us saying, like I wrote here, hey Frank, I just reacted 4.99 times 10 to the 24 atoms of iron with 5.7 times 10 to the 23 molecules of sulfuric acid, and it was a blast. A big mouthful. And chemists try to make things simpler. So what we deal with is large amounts called the mole. So we're linking the small atomic level up to our level. The small number of particles, the large number of particles that are very small, up to masses that we can see. Look, there's my carbon structure, very simplified and naive, up to my diamond. Ooh, pretty. Okay. So it's about scaling up. So in this chapter, I've been talking about our example reaction between aluminium bromide and potassium, leading to potassium bromide, the in inverted commas, molecules, because it's ionic, of potassium bromide and aluminium. So what I've done here is on the right, I've kind of drawn a representation of that reaction by the least number of particles. So I've got my one base unit, even not an ionic compound, of aluminium bromide, and my 3 atoms of potassium. That leads to 3 of these base units, because it's ionic as well, of my potassium bromide, sorry, I'm just losing myself, and my 1 atom of aluminium. So there's the smallest kind of unit possible, our balanced equation. Alright, so what I can say is the same ratio occurs when I introduce, if I've got a dozen molecules of aluminium bromide, or a dozen units of aluminium bromide, are going to react with 3 dozen atoms of potassium. And they're going to produce, what's left over when it's done, is 3 dozen of those base units of potassium bromide and 1 dozen units of aluminium. So all we've done is multiplied the ratio there, and we've just got a lot more, but it's the same reacting ratio. But now we're talking about dozens. And you can do that with 1,000,000 as well. If you multiply that whole kind of balanced equation stoichiometry by 1,000,000, it will mean that 1,000,000 molecules of aluminium bromide reacts with 3,000,000 atoms of potassium to produce 3,000,000 molecules of potassium bromide and 1,000,000 atoms of aluminium. So we're just scaling and scaling and scaling. And by the time we get to millions, we're still dealing with such a small amount of matter that's not practical at our level. So we've got to go much bigger. And we reach a point, and we'll introduce that point soon, where we talk about, instead of the dozen millions, we're going to talk about a much larger number called a mole. And it means that, for our example, 1 mole of aluminium bromide reacts with 3 moles of potassium atoms to produce 3 moles of potassium bromide and 1 mole of aluminium atoms left. So the ratio, that stoichiometry of the 1 to 3, 3 to 1, still exists, but we've multiplied it up. And we've reached a number called the mole, where, hey, suddenly we've got amounts that we can see and we can pick up with a spatula, and we can capture in a balloon if it's a gas. And, and we couldn't do that if it was a dozen or 1,000,000 or something around there. It was still too small. So we picked a very large number. Okay. And one of the problems too was, and why we can't use other units like grams to weigh things out, well, we can, but it's not practical to a chemist so much, is that all the elements weigh different amounts. We've got different numbers of protons and neutrons there, and we have got different numbers of electrons, but that doesn't mean too much, because remember, there was it 3,000th of the mass? Anyway, so here I've got a diagram where I've kind of got a representation of a hydrogen atom and a uranium atom, showing that the uranium atom is much, much larger, okay? And we can't compare their masses. We can't compare their masses so much because in my little representation here, my diagram, on the left, I've got a certain amount, a certain mass, 1 gram of our hydrogen, and there's a lot of hydrogen atoms in there, okay? But if I take 1 gram of something heavier, like uranium, there's a lot less atoms in it, yeah? They're a lot heavier, so there's a lot less atoms of uranium in 1 gram than there is of hydrogen in 1 gram, because hydrogen weighs a lot less. We've got one proton in the middle, plus that measly electron. But in uranium, we've got, 293, 298 mass units. Neutrons plus protons, so they're much, much, much bigger, okay? So therefore, we also needed a system to get around that mass problem, where 1 gram of one atom does not, well, it weighs the same, sorry, I'm going down the wrong way. Let me start again. 1 gram of one atom contains a very different number of atoms of 1 gram of a completely different atom. They weigh different amounts, okay? So what happened then, early chemists worked this out, and what they did is they tried to formulate and calculate relative masses, okay? So the mass relative to another. So they compared the masses between two without knowing the exact mass, but they could tell that a mass of this atom was a certain times the mass of another one, okay? And so what they did, one of the people working on it was this guy on the right here, Amadeo Avogadro. And yeah, remember you heard his name earlier? Yeah, he's important. So he was one of the early chemists to work out the mass difference between these atoms, okay, between these elements. Couldn't work out the exact mass, but he could work out the mass difference, okay? It's called the relative atomic masses, okay? And what he found out is that if you did it a certain way, you get a very pretty result. You get nice even integers out of there. So him and a few others, when they set carbon to equal 12 units, they found that, the mass of hydrogen was 1/12 of that, okay? And they saw that beryllium was 9/12 of that. And so what I've done here on the right, I've done this diagram. Let me swap back to the pencil. And so I've set the mass of carbon to 12 arbitrary units, and the relative masses of all these other elements we've calculated here. And you'll notice that hydrogen is just a touch over 1, and helium is 4.00, another nice even number. Lithium is quite close. Beryllium's right on 9. Nitrogen is just a touch under 14. Oxygen's just a touch under 16. Fluorine's just a touch under 19. And look at these other near integers higher up. That's a very pretty result. And it kind of gave a clue that matter came in chunks or was quantized, yeah? So matter, you gave predictable numbers and integer values. It's a very, very beautiful result. And so he did a lot of work on these relative atomic masses, but then he died. I don't know if it was old age, but later work came to build upon his earlier work, okay? And he was honoured in such a very large way. Okay, so the mid-18th century chemists decided they needed a new unit, a new number of these. And it will be the number of atoms of carbon in 12 grams, because that 12 grams and 1 gram of hydrogen, and they knew that hydrogen was the lightest element, so that 1 to 12 ratio was really pretty, and it gave really good results. So they said, let's find out the number of atoms in 12 grams of carbon, because it's a nice easy number, because then if we're comparing this, there'll be the same number of particles in 12 grams of carbon. There'll be the same number of particles in 1 gram of hydrogen. Okay? So, however many particles there are in 12 grams of carbon, there'll be the same number of atoms in 1 gram of hydrogen. Okay, so that relative atomic mass. They just needed to find out this magic number that linked them. And they could have chosen any number. They could have set this, the amount, they could have said, hey, we're going to do 13.314 grams, find out how many. And it wouldn't have mattered. We'd have a different number for the mole and it'd all work out. But why not make it pretty? Why not make it, give it these values that link and show relationships? Okay? So the mole is this number of atoms in carbon, of carbon in 12 grams, and it's also the same number of atoms of hydrogen in 1 gram. Okay, so the chemists then were now hunting for this number, and it took over 50 to 60 years and a variety of scientists. But finally, in the early 1900s, this number was very accurately determined, and they named it after Amadeo Avogadro. So it's called Avogadro's number, sometimes Avogadro's constant. Okay, so they called this number the mole. We have a mole of this, a mole of that. And the number of particles that are in there is called the Avogadro's number. So that's why I got the little mole there. And in my diagram, I've got a very crappy image of a hydrogen ampule on a set of scales with 1 gram there. Obviously badly put together, but it's my talent. And 12 grams of carbon on there. Okay. So the number of hydrogen in 1 gram, 1.00 grams, and the number of carbon-12 atoms in 12 grams is a number we call Avogadro's number, after this guy here, okay, for his work, although he didn't actually find the number. And so this number turns out to be this very, very long number. There's a lot of atoms in 12 grams of carbon, isn't there? 602.214.13 blah 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 000. We simplify that in scientific notation to this very important number that every chemist loves. 6.02 times 10 to the 23. Sometimes you might say it as 6.022 times 10 to the 23. And that's how many particles there are in a mole of something. So if we're talking about a mole of carbon, we're talking about 6.02 times 10 to the 23 atoms of carbon. Okay, and that's particular to the carbon-12 too. And we can say that if you have hydrogen 1, or the hydrogen with 1 proton in the middle, it has an atomic mass of 1.00 grams per mole, because 1 mole of that weighs 12.00 grams. Okay, so here, important definition. The mole, sometimes abbreviated like meters, is abbreviated to the little m. We can't just use the little m, it's taken by meters, the length unit. So it's MOL usually when we abbreviate it. The mole is a number that relates the molecular or atomic mass to a constant number of particles, okay? It is defined as the amount of a substance that contains as many elementary units as there are atoms in 12 grams of carbon-12, which is 6.022 times 10 to the 23 atoms. 6.022 times 10 to the 23 is known as Avogadro's number. So 1 mole of particles contains 6.022 times 10 to the 23 particles. Okay. Particles is very broad, and we use the mole unit to describe different things in chemistry. In general, we'll call them particles, but if you want to be a bit more specific in particular examples, we can apply moles to number of atoms, number of molecules, number of ions, or when we're talking about ionic solids or liquids if we're going there, but that's quite unusual, or these formula units for ionic compounds, such as the NaCl, that repeating unit. We can talk about moles of repeating units. Okay, so if we look at the periodic table, there's a lot of info here, and the masses on there are given in grams per mole. I know earlier we talked about atomic mass units and all that kind of stuff, but from now on, I want you to think of these mass units given on the periodic table as grams per mole. It's telling you 1 mole of this atom would weigh this amount. So 6.02 times 10 to the 23 atoms of carbon-12 weighs 12 grams, or carbon-12 weighs 12 grams per mole. Let's skip down a bit. 6.02 times 10 to the 23 atoms of 28 silicon, that isotope of silicon, weighs 28 grams. So silicon 28 weighs 28 grams per mole, and so on. So those units that you're looking at before are now grams per mole. We chose that mole unit to make it nice and even. Okay, look at these 2 images that I found online. The one on the left is showing us a mole of different elements. Okay, here we've got a mole of zinc, and it's 65.4 grams, because zinc weighs 65.4 grams per mole. So whoever took this photo has just weighed out a mole of all these different elements. There's your 12 grams of carbon, there's your 24.3 grams of magnesium, and there's your 63.5 grams of copper. There's your sulfur, there's your silicon, there's your lead, and there's your tin. All of them weigh different amounts, but they have the same number of particles in them. 6.022 times 10 to the 23 atoms in each one. Same number of atoms, but because atoms weigh a different amount, they weigh a different amount. Okay? And here's a different one, and I put this in here because we've got a liquid in here. So we can talk about the mass of a liquid, so we can link it through density. And we've got a volume of gas in that balloon. All of these contain the same number of atoms. Okay? Hopefully that helped. Watch it again if it didn't, but there's also some good videos here. 2 Tyler DeWitt ones, a Bozeman Science Professor Dave is good, and a good old TED Ed one. How big is the mole? Always really good. So they can give you some extra help, probably explain it better than me. Okay, what I'm going to do is leave it there and pick up the second one, where we're going to take this mole kind of unit and start to put it in practice. Start to do some actual mathematics and chemistry with it. So thanks for joining me, and come join me for the second video. There'll be a bit of a pause there. Catch you next time.